In this video, I explain the concept and empirical motivation for panel autoregressive distributed lag cointegration modeling. And in the video that comes after this, I'm going to use eViews to show a working example of how to estimate such dynamic heterogeneous panels. Examples of panel data are shown here, beginning with balanced panels, which may be symmetrically balanced, as in this first example. A short panel in which number of time periods is less than the number of groups in the panel, and the long panel where the number of time periods is greater than the number of groups. A balanced panel is the case where the number of observations is not the same across the groups. Now, but in panel ARDL modeling, we're going to be dealing with dynamic panels in which the lag term of the dependent variable is included as regressor. As a reminder, in the ARDL error correction framework, regressors can consist of a mix of I0 and I1 variables. In other words, variables that are stationary at level and those stationary at first differences. They can also be all I0, all I1, but certainly nothing I2 or greater. And the parameters of interest are going to be the long and short run coefficients, and importantly, the speed of adjustment. Now, the empirical process is summarized here. So we're going to begin with running a panel unit root test to confirm that no variable is I2 or greater, and then number 2, specify panel ARDL cointegration model, and 3, estimate the model using one or more of these estimators, which I'm going to talk about shortly. And in the case where you use a couple of these, you can certainly use the Hausman Test to determine the appropriate estimator and interpret the results. And at that point, you're going to be talking about joint cointegration among the variables, discuss speed of adjustment to long run equilibrium, which is going to be the coefficient of the error correction term, and then discuss long run and short run causality. To understand the modeling framework, the unrestricted specification for the ARDL system of equations is shown right here, which among other things includes the group specific fixed effect error term omega. The dimensions of the coefficients and the variables are summarized right here. By reparameterizing the model, we come up with the panel ARDL vector error correction model, which shows the short run terms in blue and the long run terms in red. The short run coefficients with which to infer on short run Granger causality are lambda and delta, while the long run coefficients are phi and beta within the long run representation in the model. Importantly, beta right here will help us infer on long run causality for each regressor, while phi will be configured to measure the speed of adjustment to long run equilibrium. All the coefficients are defined right here. In the manner explained in the 1999 study by Pesaran, Shin, and Smith, we can derive the error correction model from this long run model shown right here, a bivariate model. The ARDL specification with one lag for each of the two variables is shown right here. Now, if we redefine the two variables y and x in the manner shown here, and as you can see that it all solves out to become y and x. Now, if we do that and substitute, we work our way toward obtaining the error correction model, which after simplifying and slightly rearranging terms, we're going to come up with this ECM right here, this error correction model. So you can pause the video a little bit and enjoy going over it. So in the ARDL error correction model, this term in brackets, that's our error correction term. And the coefficient right here is the speed of adjustment. So in general, the Panel ARDL vector error correction model consists of those two components, the short-run component in blue and the long-run component in red, which shows the speed of adjustment as its coefficient. And this long-run component is in fact the long-run representation within the error correction model. So the question becomes, how do we estimate the model? The three key methods discussed are dynamic fixed effects, mean group, and pooled mean group. The dynamic fixed effects estimator assumes that all the coefficients, both long run and short run, are homogeneous across the groups, while the mean group estimator assumes that they all vary across the group. So these are extreme estimators. In between is the pooled mean group estimator introduced in 1999 by Pesaran, Shin, and Smith, which assumes that only the long-run estimators are the same across groups while the short runs vary. So these are explained in turns a little bit in the next couple of slides, and you can pause a little bit and go over them. The point to note again is that unlike the mean group estimator, pooled mean group constrains the long-run coefficients to be the same. And unlike the dynamic fixed effects estimator, it allows the short-run coefficients to move around, to vary across the groups. As such, the pooled mean group is based on a lower degree of heterogeneity because it imposes homogeneity, as I note here, only in the long-run coefficients, but allows heterogeneity in the short-run coefficients. And so by not imposing equality of short-run coefficients, it allows the dynamic specification, which is the number of lags included in the short-run component of the model, to differ across the groups. Now, what that means is that the number of time periods in your data set must be large enough to estimate the model, the short-run model that is, for each group separately. And so under the assumption of long-run slope homogeneity, the pooled mean group will produce estimators that are consistent and efficient. And so you might ask the question, why the assumption of long-run slope homogeneity in the pooled mean group estimation approach? Well, I put it this way. Remember that panel data consists of different groups with the same underlying characteristics. An example could be the performance of hotels in different classes, from the luxury brand down to the economy class. Now, although in the short run, these different hotel classes may react in varying degrees to changes in the broader economy or in the equity market, we can expect that the degree of impact in the long run, by and large that is, will be largely the same. And that's because for the most part, they're going to face similar budget constraints, common demographic and environmental factors, common technologies in their operations, and a variety of other common factors, not the least of which is the effect of hotel demand and availability on revenue management. So for these and many other reasons, a number of studies on Panel ARDL prefer to estimate the model right off the bat using the pooled mean group estimator. So the basic assumptions of the PMG estimator are, number one, that the error terms are serially uncorrelated and distributed independently of the regressors, and so we don't have that endogeneity problem. Two, that a long-run relationship exists between the dependent variable and the explanatory variables. And finally, that there are common long-run effects in that long-run parameters are the same across the groups. And in the case where you've decided to try out a couple of these estimators, specifically the pooled mean group and mean group, you can run the Hausman test to determine which is more appropriate under the null hypothesis that the pooled mean group is preferred in that long-run coefficients are homogeneous. And if you obtain a p-value that's less than 5%, then you're going to be rejecting the null hypothesis that the pooled mean group is good in favor of the alternative that the mean group estimator is more appropriate. Otherwise, you're going to have to roll with a pooled mean group. And in the next video, that's what we're going to do. We're going to hook it up with eViews. Hope you loved it.